Welcome everybody. We're starting a lesson on graphing exponential growth functions, and when we think about things that grow exponentially, some things come to mind. The salaries of professional athletes is always a popular one, although that one can be arguable, I guess, at times. Things that grow quickly, things that grow, nonstop. So when we talk about an exponential function, we graph it, we're really talking about things like y equals a b to the x power. An exponential growth problem would be any time in this situation when a was greater than 0, so a is a positive number, and b is greater than 1. So the number that you're multiplying by is a number greater than 1. Like I multiply by 2 every time, or 3 every time, or 4 every time. If we're talking about exponential decay, which is coming up in the next section, b would be in between 0 and 1. It ends up being in, we multiply something by 0.5. The growth factor in this situation is b. That's the number we're multiplying by every time. And an asymptote, that's a line that you get close to, but you never ever touch. And so a lot of times in our graphs, we're going to see things that have asymptotes like this. Like it comes down to this line, and it never, ever touches it. It gets close to it, but never touches it. Okay? Or when you have an exponential, that's kind of like an exponential decay, but you get the point there. So let's take a look at the parent function. We always refer back to that parent function as this is where things all begin. So the function y equals b to the x. We're not going to, a will be 1 in our situation, where b is greater than 0 is the parent function for the family of exponential growth functions with base b, of course. The general shape of the graph y equals bx is shown here, and it's kind of, people talk about it being like kind of a J curve a little bit. The domain of y equals b to the x is all real numbers. Remember, shorthand for all real numbers looks like that, kind of like the paragraph symbol. And the range is only when y is greater than 0. And if you look at that graph, you can see y is always above 0. You don't have anything down in this area down here, because your range is y is greater than 0. So what does that all mean? Let's take a look at example 1 and see if we can put some more sense to it. Y equals 1/4 times 6 to the x. Well, to graph this, a few things, a few basic things you could do if you're doing this by hand would be to just plug 0 in there for 6. 6 to the 0 is 1. 1 times 1/4 is 1/4. So I have the point 0, 1/4, which is maybe like right there. When I put 1 in there, 6 to the 1 is 6. 6 times 1/4 is 6/4 or 3/2, or maybe 1.5 is what your calculator would tell you. And so at 1 we have 3/2, it's looking like that. Well, the graph of that thing, if I graphed it by hand, and I'll try to do it just as here, kind of looks like that. I don't know if it's quite enough curved in here, but it's pretty good. You're gonna begin. You're gonna draw this where it's just above the x-axis. Above is the word you want in here, and it moves up to the right. Moves up to the right. Sorry for my terrible handwriting, but hopefully you're listening and watching all at the same time, not just writing down and having me on mute. Example 2, y equals ab to the x minus h plus k. Now let's remember that h and that k, those are shifts. Those things move to the left and to the right and up and down. So if we looked at something like this, its parent function is going to be y equals 2 times 3 to the x. And if I just graph that thing, if I put a 0 in there, I get 0, 2 Put a 1 in there, I get 1, 6. And so that would start at those points, 0, 2, and 1, 6. But then we have a translation, H and K. This minus 2 means it's going to go to the right 2, because remember the H's work just the opposite of what you might think. And the minus 2 on the K means it's going to go down 2. All right, so what's going to happen to these graphs, I'm going to graph the point 0, 2, and I'm going to graph the point 1, 2, 4, 6, and that graph would look not very good. It's supposed to be a nice J curve right through there. Would look something like that. But since we're moved to the right 2, 1, 2, and down 2, 1, 2, I now have a point here. And remember I had a point up here, 1, 2, down 1, 2. Now I have a point here. And now my whole graph has moved. And remember my asymptote right here? I had this asymptote that went across right here. That line that I got close to but didn't touch. It also moved down 2. Because if the whole thing shifted down 2, so my new graph is going to look like that. Through those 2 points, if I make my point big enough. The graph's asymptote was the line y equals 0 originally, but now it's moved to y equals -2 because it shifted down, and the domain is still all real numbers, and the range is all numbers that are greater than -2. So anytime y is greater than -2. You go ahead and try checkpoint number 1 there, and let's see what you get. Okay, so hopefully when you did checkpoint number 1 here, you graphed it using all the same tools that we just talked about. Maybe you said the original function here is y equals 2 times 4 to the x, and you graphed that and you shifted it, and you ended up with a domain of all real numbers and a range where y was greater than -3 because you shifted down. Y is greater than -3 because you shifted down 3 spots from where it was. And you went through all the same steps we did in example 1. Now, I will tell you that you could do this on your calculator. You will have to be able to explain how to do that on your calculator, but you could do this on your calculator. And let me go through that with you real quick here. So if I grab my calculator and I turn it on, and I'm going to move it over here so I can see what I'm graphing. Go to y equals, and I'm going to graph y equals 2 times 4 to the, and I'm going to put parentheses around this, x plus 1 power, x plus 1 power minus 3. And I think it'll do everything correctly if I have that in there. So as I graphed it, you'll notice this moved down 3 right here, and it shifted to the left 1. So it went down 3 and to the left 1. Let's graph that original and just make sure that that's true. So let's go down and let's graph the 2 times 4 to the x and see what that looked like. And that one should come across here and go up there. And that's exactly what it did. So you can put these on your calculator. If you want to see what points they are, you go to your table. You can see what points they go through and take a look at what happens to your y's every time they're being affected here, right? So you can take a look at each set of points all the way down, and you might notice a little pattern there as we go. So great tool to have, that table. All right, let's take a look at example number 3 here. Example number 3 says, Buffalo in the last 12 years had an initial population of 38 buffalo, and a state park grew by 7% a year. That would be an exponential growth. You have, 7%. It's kind of like when you put money in the bank. It's an exponential growth. Write an exponential growth model given the number n of buffalo after t years. About how many buffalo are in the park after 7 years. Well, the initial amount of buffalo, A, that's the amount that you're going to start with, remember, 38. All right? And the percent increase was 0.07. Well, if you increase 0.07 every time, then your multiplier is 1.07. You just add 1 to that 0.07. We have this nice little equation, right? The exponential growth equation. They gave that to you right here. So I end up with 38 times 1.07. And how many years was that again? Oh yeah, 12 years. And so I'm going to take it to the 12. And if I grab my calculator real quick, that's for some reason I put away. Grab my calculator real quick, and I go ahead and put those numbers together. So I had 38 times 1.07 to the 12. So over here on my calculator, I have 38 times 1.07 to the 12th power. And I end up with 85.58 buffalo after 12 years. So if I come back over here and I write 85.58, well, you can't have 85.58, right? So you're going to end up with about 89 buffalo. Now this is what's happened over the last 12 years. And so the initial population of 38 it had a growth of 7% over the last 12 years. That's not what they're asking us to do here. They didn't ask us to put 12 in here. They asked us really just to put t in here to give us an equation. So when we're looking at this, we're really just looking at 38 times 1.07 to the t power. All right? And then using this model, you can estimate the number of buffalo after 7 years, because that's the question they're asking in A, right? So the number of buffalo that I'm going to have after 7 years is the same problem, but instead of 12, I'm going to put 7 in there. So I'm going to have 61 buffalo, approximately. So I come back over here, and I put all that together, and I have 61 buffalo. Now, the graph, when I graph this thing, if I had 0, if nothing happened, if no time passed, how many buffalo would I have? I think everybody in the room would say, of course, it's got to be 38. Nothing happened. You have 38. Nothing happened. You still have 38. That makes sense. If I put 1 in there, then I have that 1.07 times 38, because 1.07 to the first power. So when I go back over my calculator and I do 1.07 times 38, I get approximately 41 buffalo, or 40.66 buffalo. Now, it doesn't make any sense to say we have 40.66 buffalo if that's what you're asked, but for graphing purposes, we are going to use 40.66. So we have 0 and 38. Looks like it's about right there or so. And we have 1 and 40.66 right there or so. And so as you graph this thing, you got to be very careful. This is going to be an ever so slight graph. I don't know that I would pick these 2 years so close, because in B it says graph the model, use the graph to estimate the year where there were about 53 buffalo. I don't know that this graph 1 year and 0 years and 1 year is going to give me a very good estimate of that. But let me show you a cool trick you can do in your calculator that's going to give you an excellent estimate of that. In your calculator, we can graph that scenario. We can have 38 buffalo times 1.07 to the t power. We're going to call it to the x power. And when I graph that, my window's got to look like this a little bit. So on my window, on my x's and my y's are okay, but my y's have to go up to like 100 to give me a better picture of what that's going to look like. And this is the graph from 0 to 10 right here. So while that doesn't help you a lot, what if I go down here and I say, when are we going to have 53 buffalo? When's y going to equal 53? Well, right here in this spot, right in this location, that is when you're going to have 53 buffalo. So if I do second calculate and intersect between my first curve and my second curve, look at there. After 4.9 years, or approximately 5 years, I'm going to have 53 buffalo. So that's a great way on your calculator to get that problem solved. So we said approximately 5 years, and we graphed it all right on our calculator. So that was a great help to us. Compound interest. Anybody who wants to be rich out there, show your hand if you want to be rich. All right, I didn't see any hands, but I generally don't see much from here. Everybody would like to be rich, right? Not everybody's willing to work that hard, or not everybody makes that their lifelong goal, but money couldn't hurt you, I'm sure. So this equation right here, this is how rich people get richer. They put money in the bank, it gains interest, and then you get interest on top of interest. So it's called compound interest. You will need to memorize this formula. The amount of money that you have equals the principal times 1 plus the interest rate that you put it in the bank for, divided by the number of times a year it's compounded, like monthly would be 12, to the number of times it's compounded by, times the number of years it's in there. So let me show you how that works in a real problem. Like example 4 here. In example 4, you deposit $2,900, that's your principal, in an account with 3.5%, that's your interest rate, and what's your balance going to be after 1 year if it's compounded monthly. That's how many times that it's been compounded. So we have, as an equation, 1 plus, now 3.5 is a percentage, so I'm going to call it 0.035 divided by the number of times it's compounded a year, 12, to the 12 times the number of years, which is 1 power. So if I put all that into my calculator, let's grab my calculator again, and we have, quit out of this, and I have 2,900 times 1 plus 0.035 divided by 12 to the 12th power. And that means after 1 year at 3.5% interest, I'm going to have $303.14 in the bank. Well, that's a pretty good deal. I didn't do anything. I just put my money in the bank, and I made a good chunk of change. So let me come back over here. And I had $3,003 after a year. Pretty good deal. With the interest compounded annually, the balance after 1 year is what? So if you didn't get it compounded every month like we did, you got it compounded annually, what do you have? Well, if I just took my $2,900 and I didn't compound it at all, then I'm just looking at 1 plus 0.035 to the first power, which is what it is. All I end up was $301.50. So over here, I end up with $3,001.50. And although it doesn't seem like a lot, we only made a couple more dollars here, it is going to be a big deal in the long run if you keep getting interest on top of your interest. All right. Well, you guys go ahead and do checkpoint 2 and 3. and I will tell you, I'll get back to you in just a sec. All right. This one here, the answer was about 80, approximately 80. And this one down here was 5, 5, 8, 7, 4, 5. I hope you got those answers. If not, we can talk about it tomorrow. Have a good day, folks.